Welcome to Complex Analysis. Today, we are going to explore two of the most fundamental and powerful ideas in mathematics: continuity and differentiation. We will build these concepts from the ground up, understanding not just the abstract equations, but the physical intuition behind how complex functions behave and shape our world. Let us start with continuity. Imagine you're walking across a vast flat field, which represents a complex plane. As you walk towards a specific destination, you measure the elevation of the ground beneath your feet. If the ground is perfectly smooth, your elevation will gradually approach the exact elevation of your destination. There are no sudden cliffs or bottomless pits. In mathematics, when a function behaves this smoothly, without any sudden jumps or breaks, we call it a continuous function. It allows you to smoothly glide into your destination from absolutely any direction. Now that we understand what continuity feels like, let us look at how it works formally. For a complex function to be considered continuous at a specific point, it must pass three strict tests. First, the destination must actually exist. The function must have a defined value there. Second, as you get closer to the target from any direction, the output must approach a single predictable number, which we call the limit. Third, and most importantly, the value you expect to get as you approach must be the exact value you actually get when you step on the point. This brings us to the mathematical equation for continuity. Conceptually, this formula simply states that the expected approach perfectly matches the actual destination. Let us break down the symbols. The variable z represents our moving input point on the complex plane, while z0 is our fixed destination point. The left side is the limit, describing the process of shrinking the distance between z and z0 down to 0. The right side, f of z0, is the actual output exactly at the destination. If z approaches from a different angle and gives a different result, the equation fails and the function is broken. Before we move on, let us see this with a concrete example. We want to determine if the function f of z equals z squared plus 1 is continuous at the specific point z equals 2i. We need to check if the limit matches the actual value. First, we calculate the exact value by plugging our target point directly into the function. We substitute 2i in place of z. Squaring the 2 gives us 4, and squaring the imaginary unit I gives us I squared. This finds the exact elevation of our destination point. Continuing with our calculation, we know from basic complex algebra that I squared is always exactly equal to -1. By replacing I squared with -1, we multiply to get -4 and add 1 to arrive at a final actual value of -3. Now we must find the limit as we approach from afar. Because polynomials are smooth, we can evaluate the limit by direct substitution. The limit yields -3, which perfectly matches our actual function value. Physically, this means there is no hole or jump here. You can safely arrive at the expected value. Now that we understand continuity, we can explore a much stricter concept called differentiation. Imagine you are standing on that same flat field and you want to measure the exact steepness or slope of the ground beneath your feet. In standard one-dimensional calculus, you can only step forward or backward. However, on the two-dimensional complex plane, you can take a tiny step north, south, east, west, or along any diagonal. For a complex function to be differentiable, the measured steepness must be absolutely identical no matter which of the infinite possible directions you choose to step. This strict requirement leads us to the fundamental formula for the complex derivative. Conceptually, we take a tiny step away from our starting point, find the difference in output, and divide by the step size. Let us look at the symbols. F prime of z represents the derivative, the final uniform rate of change. The symbol delta z represents a tiny step, which is a complex number with its own physical length and directional angle. The limit forces this step size to shrink to 0. If this results in a single consistent number, regardless of the approach angle, that number is the derivative. Let us visualize what this tiny step looks like. In this diagram, you are looking at the complex plane with real and imaginary axes. The central point is our target, Z. Notice the arrows pointing inward from every possible direction: north, south, east, west, and all the diagonals. Each arrow represents delta Z shrinking to 0. In standard real number calculus, we only had to check the left and right sides. But here, the limit must survive the ultimate test of infinite directional approaches. This is exactly why complex differentiable functions are so rare and mathematically special. Now that we have the formula and the visual intuition, let us calculate a derivative from scratch. We want to find the derivative of the function f of z equals z squared. We need to prove that this function has a consistent rate of change, regardless of the direction we move. We start by plugging our specific function rule, which is to square the input, into the general derivative formula. We replace the generic input with z plus delta z squared and subtract the original function z squared. This setup is the universal starting point. Continuing with our calculation, we expand the squared binomial in the numerator using standard algebraic rules. This reveals 3 separate terms, allowing us to see exactly how the tiny step interacts with the original position. Next, we notice that the positive z squared term and the negative z squared term perfectly cancel each other out. This removes the static parts of the equation, leaving only the terms that contain our tiny step variable, delta z. This simplification is exactly what we need to eventually eliminate the fraction and avoid dividing by 0. For our final steps, we divide every remaining term in the numerator by the denominator delta z. This crucial step eliminates the fraction entirely. Because the fraction is gone, we are no longer in danger of dividing by 0 when we apply the final limit. Finally, we let the tiny step shrink to exactly 0, causing the second term to vanish completely. This leaves us with a final clean derivative of 2z. Because this result does not contain any directional angles, it proves the rate of change is identical from every approach. You might wonder why we care so much about this strict directional rule for derivatives. When a complex function is differentiable everywhere in a region, it earns a special title, an analytic function. These functions possess magical properties, such as preserving the exact angles of intersecting lines when mapping shapes. In the real world, engineers and physicists rely on these functions to model two-dimensional fluid dynamics, like smooth airflow over an airplane wing, or to calculate invisible electromagnetic fields. Without differentiability, these physical models would break down into chaotic turbulence. Let us review the key takeaways from our journey. First, continuity ensures that a complex function has no sudden breaks or missing pieces, guaranteeing a smooth path to any point. Second, differentiation is a much stricter upgrade, demanding that the function's rate of change is perfectly identical from every possible 360-degree angle of approach. Together, these concepts form the bedrock of complex analysis. They filter out chaotic equations and leave us with only the beautifully structured functions that govern the laws of physics and engineering. You now understand the foundation of complex behavior.